students. You're welcome.
Akimo's Educational Online Services, and today we'll be looking at a topic that will be a very fascinating one, and the topic we did already with the subject chemistry. Lest I forgot, my name is Mr. Samson, and I will be your tutor today, guiding you on the demonstrative or practical aspects of chemical reaction. Of course, we discussed this topic last week or in our last lesson, where I was looking at the various types of chemical reaction. But before I looked at that various type of chemical reaction, we tried to attempt balancing of chemical reaction, which we did so, and I believe you enjoyed that class. For those of you who are not in that class, I would advise that you go back to that very episode, click on the platform, and then look at that lesson once again before you can ascertain to this other part of the practical. Now, for those of you who are in SS2, SS3, I would advise that you also partake in this class, because it will be know that your exam is fast approaching. Despite COVID-19 has come, the exam is fast approaching, and before you know it, it will be a practical section. So you stay very well and watch the class and enjoy the class. So very quickly, let's look at the practical demonstration of chemical reaction. In our last lesson, we talked about the different types of chemical reaction. When we say we have combination reaction, we have decomposition, which is the opposite of combination. We have displacement method, we have oxido reduction or redox reaction. We also have exothermic and endothermic. Now, in the last class, I did not explain this one. Before we go into the demonstrative aspect of chemical reaction, I think I need to look at this aspect, these four subsidiary ends, which are the displacement reaction, once again, double decomposition, catalytic reaction, exothermic and endothermic reaction, whereas you will go home with these as assignments, so that in the next or subsequent class, we look at it thoroughly, and then we try to scrutinize all those mistakes students do in balancing redox equation. Now let's start. What is displacement or replacement reaction? Here, this reaction simply explains how an element will replace another element in a compound of that element. What am I trying to say? If I have an A reacting with B and C, then I see that this part is a reactant part and the product would be this. Now this A is coming to replace B. Alright? Now B is a compound that is made up of B and C. Now A is coming to replace B, where we have B, A, C, and then that A would display the B out or replace the B. That's where the names come. Displacement or replacement reaction. A typical example of this is when we have a metal trying to replace another metal in a metallic compound. Now, this reaction or displacement reaction, as the name implies, is of utmost beneficiary to scientists and chemists who try to look at the reaction between metals and a compound, or who try to look at the experimental aspect of chemical or equation, or the experimental aspect of chemical reaction. Now, in displacement reaction, we can look at that this might be a metal, and this B might also be a metal in a compound to give a metallic compound and another B which has been displaced already. Now, I want to look here like a typical example. Let's say zinc. We always try to display copper sulfate to have zinc sulfate plus copper. This is what I was looking at. A stands for zinc, while Cu, which is copper, stands for the B, and then the sulfate C. Then we have zinc sulfate and then copper. Now this has been used by chemists to look at what we call activity series. What is the meaning of activity series? This simply explains when a metal in the highest order of the series display the metal in the lowest order of the series. That's what we are looking at when we look at a compound being mixed. For instance, I gave a mnemonics before in our last class, and I gave a simple mnemonics which was given in this format, like the popular scientists can make a zoo in the low humid country most satisfactory, where I say each of those words I've mentioned stands for, from the first one, potassium, sodium, calcium, magnesium, aluminum, zinc, and the rest of them. I want you to go back and look at that activity series. It means that if you focus on that activity series, you will agree with me that the metals that are evenly distributed in the upper part of the series can display that of the lower part of the series. What am I trying to say? It is experimentally wrong. For instance, if we see the preparation of hydrogen, you find out that hydrogen can be prepared when we have zinc, which is the metal in the iron activity series, with hydrochloric acid. It means that from here, zinc can display hydrogen of forming zinc chloride, and then hydrogen is being given up. Remember, this is not a balancing chemical equation. Go back to your balancing chemical equation and then you try to balance it. It means that zinc, which is found in the activity, the upper activity series, can display hydrogen to give what? Zinc chloride, and hydrogen gas is leaving up. Any gas or any metals that is below hydrogen in the activity series will never react with any compound to display hydrogen. Now, if you want to look at it practical, we have hydrochloric H2SO4, which is sulfuric acid, and then you add zinc granules to it. There is always an exothermic reaction. Heat is given off to the environment, and we find out that the zinc will mix evenly with the tetraoxide 6 acid to generate hydrogen gas. Before you can know that it's a hydrogen gas, you must have to carry out a test. That is the flame test, to look at how hydrogen, the behavior of hydrogen, where it gives a pop sound. That's not what our topic of discussion is today. Now let's go to the next one, double decomposition. From the word double decomposition, this has to do with two compounds that are in aqueous form. Aqueous, remember I told you that aqueous means when a compound is being dissolved in water. When two compounds that are in aqueous form are mixed together, you find out that there is a tendency that one which was a solid, that it was a solid that was dissolved in an aqueous form of another compound, tends to become insoluble, trying to settle in the aqueous one, and then we say that process is what? Precipitation. It has precipitated. A typical example of this double decomposition, let me use the alphabet, the denotation. Let's say we have AB, a compound AB, plus compound CD. AB and CD. You'll find out that there is always a combination, a decomposition of A, B, and a decomposition of C and D. A will react with D, whereas B will react with C to form AD and what? BC. It means that in a decomposition reaction, there is a total removal or combination using ionic formula. But when we look at a typical example, you see what I'm trying to do. Now, A will react with D to give another compound AD, and then B will react with C to give another compound which is BC. Another typical example I will look at is this. In regards to double decomposition, we will consider one, precipitation reaction. Like I've said before, precipitation is formed when an insoluble salt is dissolved in an aqueous form of another salt. Now let's look at barium chloride. Barium chloride, which is an aqueous, is being dissolved with copper sulfate. Now this is cupric sulfate, copper sulfate as the name implies. Now if barium chloride is being added to copper sulfate in a test tube, this is a test tube. Remember, I said today we'll be demonstrating, so if you're there, I am ready for you. Alright, so if we have barium chloride mixed with copper sulfate, which is blue color, copper sulfate is always blue, then barium chloride is what? Is a solution, already the transparent solution which we know. Now if barium chloride is added to copper sulfate, you always see this barium chloride coming to react with sulfates, and then copper coming to react with chloride. Now, what will be the product form? So we have barium sulfates, we have copper chloride plus barium sulfate. both of them, that's it. So if in the aspect of balancing chemical equation, please you look at critically, go back to what I've taught in the previous class, and you'll be able to balance the chemical reaction. I won't go to that because of no time. Right, we look at it, you see that iron chloride reacts with copper sulfate. This blue color would tend to change immediately. Either it gives you an undissolved substance. When it's being with barium chloride, we call it gelatinous PPT, that's precipitate, or we call it another precipitate, white precipitate, or another color of precipitate form. Now, here you see that what is formed here for barium sulfate will be an insoluble. An insoluble. What I mean insoluble, it does not dissolve in this barium chloride. This barium sulfate becomes an insoluble substance, whereas copper chloride there is present in blue color. Now this is a typical example of double decomposition. Another one, this is what we call precipitation, because this barium sulfate has resulted to a precipitate being formed in it. We'll do that practically when we are working on the table. Now the next typical example I want to look at in double decomposition is neutralization reaction. What is, you might little ask yourself, what is the meaning of neutralization reaction? Neutralization reaction simply means a reaction where a base reacts with an acid, or an acid reacts with a base to form what? Salt and water. The basic product in neutralization reaction is salt and water. Take note of that. Now let's give you a typical example of that. We see hydrochloric acid, which is a dilute form. Hydrochloric acid in aqueous form. Remember, aqueous dissolved in water. Iron with sodium hydroxide, aqueous form. Both of them, this is a base. This is a strong base and this is a strong acid. We'll explain that concept when we look at salts and acid and salt. Now, sodium hydroxide, we are reacting with hydrochloric acid. Remember from our equation, hydrochloric acid, hydrogen now will react with OH, then chlorine will react with what? Sodium to form sodium chloride. This is it. The product is sodium chloride and H2O. Now this is another typical example of double decomposition with that process called neutralization reaction. So here we find out that hydrochloric acid in aqueous form reacts with sodium hydroxide in aqueous form to give sodium chloride and water. Sodium chloride becomes a salt, whereas H2O becomes what? Water. Now I'll move over to catalytic reaction. From the word catalytic reaction, it means a catalyst. Now this reaction involves a catalyst. Now what is a catalyst? A catalyst might be organic or inorganic. Now a catalyst is a substance that speeds up the rate of chemical reaction. At the end of that reaction, the catalyst is not being used. Now a typical example of a catalyst is manganese 4 oxide used in preparing carbon 4 oxide when potassium trioxochlorate 5 is being decomposed. I will do that on the board and you will see. Now like I said before, we say we have two types of catalysts. The catalyst might be inorganic catalyst. A typical example, manganese 4 oxide. Let me write that on the board. Manganese 4 oxide, this is it. Then we also have another one like KMnO4 becomes an oxidizing agent. Let's not go into that. We have manganese 4 oxide. Then we also have an organic catalyst. A typical example is light. Light becomes an organic catalyst. Do you know that? Light, when we are looking at methane reacting with any of the halogens, chlorine, in the presence of UV, which is ultraviolet ray or ultraviolet light, can produce a product. That light alone is an organic catalyst. Even in our body we have them. Enzymes are referred to what? Organic catalysts. The enzymes that will convert your glucose or your carbohydrate, that is a complex carbohydrate, to break it down to glucose. For example, we say we have exose kinase, glucokinase, and the rest of them that we can see in biology in glycolytic condition or glycolytic processes or metabolism and the rest of them that will give glucose. I'm not here to discuss about that, but we are here, remember, to look at what? Chemistry of chemical reaction. Alright, so let's go to the next one. That catalytic reaction, I would like to consider the inorganic part, which is a typical example. I would say CHLO3, this is potassium trioxochlorate 5. Go and check the oxidation number, I will take you that. Potassium trioxochlorate 5 with the help of manganese 4 oxide, no heat is applied. Now there's a difference between, there's a typical difference between thermal decomposition and catalytic decomposition. Here, if you can see, in our last class we look at thermal decomposition where heat is being added. But in this case, heat is no longer added. It does not require heat. But it only requires manganese oxide, which is a catalyst. Now, if that catalyst reacts with this potassium trioxochloride 5, it will decompose this thing without being used in the chemical process. Now, what am I looking at here? I look at this has been decomposed to have potassium chloride and oxygen as a gas is being given off. Now, potassium chloride has been decomposed to have potassium chloride, and then oxygen is being given off. Now, you balance the chemical reaction, you see what it means. It means that if oxygen is 3, you add 3 here. So it means that oxygen here is 6. So I must add 3 here and also add 2 here. So this becomes what? A solid or aqueous added to this, and then we have aqueous and the gas is being given off. Now, this is a balanced equation when potassium chlorate undergo a catalytic reaction with manganese oxide to yield potassium chloride and oxygen as a gas. Now that ends it for catalytic reaction. Now we look at exothermic and endothermic. The word exothermic and endothermic means, from the word exo, it means outside. The word endo means inside. Let's start with exothermic reaction. This is a type of reaction that when it takes place, heat is evolved to the environment. It happens in our life. It happens in the environment. For instance, combustion. When we say combustion is when oxygen is being added, then heat is being evolved. Now, in every fossil fuel that you see burning of anything we see, that fossils that generate heat, that process is exothermic reaction. Here in the laboratory, we try to look at endothermic reaction in vivo. When I say in vivo, outside. So from the word exothermic, it means heat is generated to the surrounding, and from the word endothermic, heat is being absorbed from the surrounding. Now we look at this exothermic and endothermic reaction critically with a typical example. Now, a typical example of exothermic reaction is when zinc as a metal is added with copper sulfate. You find out that in that practical demonstration, you see when you stir the zinc added to copper sulfate, zinc plus copper sulfate. Remember, copper sulfate is blue. What we have there is zinc sulfate plus the copper which has been displayed out. This is the process. We looked at this before. That's when we consider displacement reaction. Now, if you look at this, we'll do it in practical demonstration. This zinc will display copper, and if you look at touch the body of the glass or the glassware used in performing that practical demonstration, you agree with me that the glassware will begin to get hot or warm. It means that heat is being evolved to the environment. Another one is when you have a sodium hydroxide pellet. A pellet is not just a liquid, but in a solid form, in a crystal. It looks like a crystal form, but not. Alright, we'll see it there when we look at it in the demonstration aspect. Now, when you have a sodium hydroxide pellet, which is a base, and then you add water to it, heat is always generated. We all do that here in our class. Alright, so for endothermic reaction is when heat is given is taken from the environment. A typical example is when we are using ammonium chloride. Ammonium chloride add with water, H2O. You find out that ammonium chloride, when water is given to it, you balance the chemical reaction. Ammonium chloride, when water is added to heat, will get cold. That's to say, heat is being taken from the environment into the reaction. That will break this ammonium chloride to have chlorine and the rest of it. So that ends it for that, a summary of everything that we're looking at. Remember, I told you that the redox equation will be discussed in our subsequent class, and that topic is for the penultimate class, which is the SS3. So let's go into the demonstrative aspect, because chemistry without demonstration is not chemistry. Let's go. Now into the demonstrative aspect of the class. Now, if you look at the board, you will see questions that have been displayed for you to carry practical with. Now, the first question is: put about 5 cm³ of distilled water in a boiling tube and take its initial temperature, T1, add 4 or 5 pellets of sodium hydroxide, that is a solid one, into the water, stir the mixture, observe and record your result. Now, from that, we mean that we have our boiling tube here, and I would not like to take 5 cm³ of the volume of the water, whereas I'll just put a particular amount of the volume inside the test tube. Now, this is what we do. Now, this is a boiling tube, and I've brought in about a quantity of volume of water which I have not measured. Now, the next thing from the one, but for you, when you're doing the practical, try to use the 5 centimeter cube of distilled water. Then we add we record the initial temperature. For now, we will not record the initial temperature, but let's assume that the initial temperature for this is less of, let's say, 27 degrees Celsius. Now, temperature should be 27 degrees Celsius, or when we are recording it, because the experiment we are trying to do is look at exothermic reaction. That's what we are considering here. And you know that from the aspect of exothermic reaction, from the concept of heat, the dynamics of heat, how heat changes, the first law of thermodynamics comes into play. That is, energy cannot be created nor destroyed, but can be transformed from one medium or from one state to another state. So that implies to heat change when we are looking at exothermic and endothermic reaction. Now, we are asked to drop the pellet of sodium hydroxide. This is what a pellet of sodium hydroxide looks like. Jesus Christ. Now, this is what a pellet of sodium hydroxide looks like. This is how it looks like. Okay, so some of you who are not conversant with laboratory reagents and equipment, this is called a spatula. We use it to take out pinch of salt and the rest of solid substances in the lab. Now, this is what it looks like. This is what it means. So if I have to drop this in this water, I'll drop it. Then observe what is happening. Try to stir. This back out. I thought where I will carry it in my hands. Right now, some pellets of the sodium hydroxide has been mixed, and I'm stirring it now. Of course, sodium hydroxide would dissolve in water. Based on solubility of substances, sodium, potassium, ammonium, and the rest of this compound or elements will try to dissolve. Then when those elements, each of them, are in a compound form, they will dissolve in water. For rules of solubility in water, compound being soluble in water. Now, sodium hydroxide, from here I can feel heat. When you're doing yours, you touch the test tube, that's your observation. Find out that because chemistry practical is being reported in 3 formats. We have the test, the observation, and the inference. For the test, this is the test practically brings in your question. You write 5 cm cube of water added with 5 or about 10 pellets of sodium hydroxide. In your observation, you find out that the sodium pellets dissolve in water when mixed stirred. It will dissolve in water for some time. From the dissolution, one of those factors that you consider when you dissolve in a compound in chemistry is one, you must have to stir it. And then when you heat, it will dissolve quickly. Alright, as I'm stirring it, it's dissolving. That's your observation. Then another observation is that you touch the bottom of the test tube. And what do you find out? It's very hot. It is very hot in such a way that it was as if heat was applied to it, but there was no heat applied to it. Now, this simply indicates that the reaction that has taken place between the water and sodium hydroxide pellets is exothermic reaction. Remember, I said exothermic reaction is when heat is being given off. Any chemical reaction that demands that heat is given off to the environment becomes what? Exothermic reaction. And then we have different types of those exothermic reactions. You find out that if a system should be, or a system should be in a closed and open but you look at this is an open system. Alright? You can see heat is being exchanged between the system and the environment. So you now see that all the substance of the pellet sodium hydroxide has been completely dissolved in the water, and then heat is being given off to the environment. Now I want to find out, we want to look at the theoretical aspects of what we just said. If we are to find the heat contents of this sample, what do we do? Now, from the idea of chemistry, we know that enthalpy change, which is change in heat, enthalpy change in heat. Please look at the board. Change in heat is always equals change in the product minus the change in the reactant sign. Now this sign, change in H, means enthalpy. The enthalpy change is always the heat contents of the sample. Now the level, the amount of heat that has been evolved. Of course, we are not looking at change in heat here and the rest of thermodynamics of heat. We have to apply it so that we know the particular change in sign when we are talking about exothermic reaction and endothermic reaction. Of course, exothermic reaction will always have an enthalpy change sign with negative sign. Now, from here we see that if the products, for instance, we measure the heat content using the temperature. If the reactant side was, say, let's say 10 joules was found in the products, 10 joules for the reactant, that is the initial testing of it. Let's say 10 joules was there. And then for this product we've given off, about 50 joules has been given off. 50 joules. Let's say the reactant was 50 joules because it is measured in joules, and the product gives us 10 joules. Now if you minus 10 minus 50, you find out that it becomes minus 40 joules. That minus sign indicate that it is what? An exothermic reaction, meaning that heat has been evolved to the environment. So take note, change in heat or change in enthalpy change is equals to the change in the product minus change in the reactants. That's when you have the delta H. Delta H means enthalpy. The word enthalpy is spelled E-N-T-H ALPY. You see that in your chemistry textbook. So let's look at, consider the first experimental aspect, and we see that, we notice and observe that the sodium hydroxide pellet has completely dissolved in water and heat is being generated to the environment. That is the first confirmatory test for exothermic reaction. Now let's go to the next one. The next one said add about 5 grams of copper sulfate in a test tube or boiling tube. Heat the sample for 20 minutes, observe the gas given off, and test it with blue and red down litmus paper to check the color change. Now, in this very demonstration, we look at how we bring in cupric sulfate. Now, this is what cupric sulfate looks like. It's bluish. You can see it labeled cupric sulfate or copper sulfate, or as the name implies, copper 2-tetraoxosulfate 6. Alright, and this becomes a salt. It is a salt. Now the salt is labeled blue and it's a crystal form. Alright, so what we are going to do is take 5 grams of this salt and then put it inside a test tube. Drop it inside a test tube. A dry test tube. Now this is the test tube. We'll take 5 grams of it. For the rest of you, for those of you who are not familiar with laboratory reagents or solid samples, this is what it looks like. Now I will drop this in this. I'll drop this in this. Though I've not measured it to be 5 grams, but in your own session, try to measure 5 grams. Now I will use this and then we have to heat it. We heat it. Then after heating it for 20 minutes, when you heat this sample for 20 minutes, heat means apply heat, the source of heat. might use the Bunsen burner and the rest of it. Then when you apply heat to it, you observe the gas that is being given off. Remember in our practical session, we don't observe gases like this. What do? We just wave it and get close to it. Then when you observe, try to see if this gas has a choking smell. If it has a choking smell, it might be ammonia or chlorine gas. But if it does not, it means it's one of the acidic gases. So we will do that now. Look at it and come later, because I will like this thing. Now, as you can see, this is a test tube, and then I have a test tube holder, a Bunsen burner rested upon a gas cylinder. Now, we have done what we're trying to do here. We're supposed to use what we normally use in the lab to apply heat. All right. Now, for this substitute of it, we improvise. So we use, instead of using a Bunsen burner. And for you, if you're going for an equipped lab, use a Bunsen burner, because the Bunsen burner will concentrate the heat to the test tube. Please notice one thing. My test tube is placed slantly and not like this. Placed slantly, close to me, so that if any gas is being evolved in the process of heating, I can probably spring it out like what you see, what is coming up. If you look at the top of that test tube, you see some condensed parts. It condensed at the top. It means something is going on. Chemical reaction is taking place. And if you look at the bottom of that test tube, you find out that color change. The change, there is a change in color immediately. As the cupric sulfate is being heated, the color will change from blue to a gray or white color, indicating that all the sulfur 4-oxide gas that is being there, that is being heated up and given as a gas. Now look at what is happening. A gas is coming off. Now this gas that is being coming off, we will just do like this. You try to wave it. It does not have a choking smell. For you, you wave it and not getting your nose close to it. It does not have a choking smell. Neither does it have an irritating smell. I cannot smell anything. It means it's an acidic gas that is there. If it was another acidic gas, because chlorine is an acidic gas, and it will always have a choking smell. Ammonia and the rest of them will have. Ammonia is neutral to litmus, but it will always have a choking smell or irritating smell. Now, here we still continue to burn. Remember, it was to be burned for 20 minutes or heat for 20 minutes. Newspaper, the blue newspaper becomes down. That's to say, it's been soaked inside water, and then it becomes down. We try to see what will happen to this blue litmus paper. The gas giving off there. As we're heating it, the gas is coming up. And look at what is happening at the bottom of the test tube. The color has changed. Continue heating it up to a point where you observe a color change in the litmus paper. Now you can see from there that the litmus paper changes color immediately. From blue, you can see the blue litmus paper that was blue has changed completely to red. It means this indicates a practical test for a gas called sulfuric gas. That's sulfur 4-oxide gas. It has a tendency to change that blue litmus paper to red, indicating that sulfur 4-oxide gas is an acidic gas. Alright, now let's also test with red litmus paper. This is red litmus paper. It's a red litmus paper. The gas that is being given off change for red litmus paper. It means this gas that is being given off is sulfur 4-oxide gas. Because if you look at the decomposition, now let's go back to the board and see what happens in the board. Now we've performed the practical aspects of this copper sulfate of 5 gram being heated for 20 minutes, and then we observe that at the bottom of the test tube, we realize that the color changes from blue to gray or white color, indicating that the gas is giving off, and also the cupric sulfate, which is copper in blue color, has completely changed. Now, what is the chemical reaction or chemical reaction involving this chemical change, or chemical balancing of chemical equation involving this color change? Remember in the last class I said underneath the arrow, when you're looking at the composition reaction, when an angle is given, alright, underneath the arrow it means heat. Either you write it this way or heat is being spelled out. Now, copper sulfate being heated generates what? Copper plus what? SO2. Now, this is copper sulfate, cupric sulfate, or copper 2 tetraoxosulfate 6 being heated. And what type of chemical reaction is this? This is what we call thermal decomposition. Remember, we have A being decomposed to give B and C. Here we have a solid. This solid becomes what? A residue. A white residue. White residue which was observed in the bottom of the test tube. This is white. The copper changes its color immediately to what we have here. And then whereas the sulfur 4 oxide was the gas that we were trying to wave away to observe. So this becomes what? A gas. Now you balance the chemical equation from here. We know that oxygen here is 2, so it means 2 must be applied here. 2 multiplied with 2 oxygen, it gives us 2. Then if copper is 1, copper is 1 here, copper is 1 here. So this gives you what? A balanced chemical reaction for that very practical processes. Now let's go to the last one, which is add some volume of barium chloride